Hello, welcome to Module 27 of the course on application of spectroscopic methods in molecular structure determination. We have some more portions to cover in the infrared spectroscopy. In this module, we will talk about the important functional groups such as carbonyl functional group, nitro functional group, nitrile functional group, and so on. Now, carbonyl functional group is a very important functional group, and the carbonyl group appears in several different functional groups such as ketones, aldehydes, esters, carboxylic acids, amides, and anhydrides. Now, the carbonyl stretching frequency appears as a very intense band in the infrared spectrum that one cannot miss its presence or its absence in the infrared spectrum. The carbonyl stretching frequency appears in a narrow region of 1850 inverse centimeter to about 1600 inverse centimeter. Although it is a fairly narrow region, each one of the carbonyl functional group has its own unique place in terms of the nature of the carbonyl functional group. Let us take the example of this particular molecule. It is a steroidal skeleton. This has an alpha beta unsaturated ketone. It has a saturated ketone as well as an ester functional group. Now, the functional groups are color coded, and the corresponding frequency of the carbonyl stretching frequency is also color coded. For example, the alpha beta unsaturated carbonyl functional group comes at 1660 inverse centimeter, whereas the saturated carbonyl functional group comes around 1735 because it is a ketone, and when it is in the form of an ester, it comes even at a higher frequency of 1760. So from the infrared spectrum, you get a wealth of information as far as the carbonyl functional group is concerned. Now, in the right hand side, there is a similar structure, except one more carbonyl is added to distinguish between an open chain ketone and a cyclic ketone. This is a cyclic ketone. Cyclic ketone can be distinguished from the open chain ketone by the different frequency that it appears in the infrared spectrum. So, although it looks like a narrow region, the carbonyl functional group is a fairly well defined functional group in terms of the stretching frequency that it comes in the infrared spectrum, depending upon what kind of carbonyl functional group we are discussing. Therefore, every type of carbonyl functional group has its unique place in the infrared spectrum. This is further described here. The base value for the carbonyl stretching frequency in various types of saturated carbonyl functional group is given here. For example, anhydrides have two bands. One is because of the symmetrical stretching, the other one is because of the asymmetrical stretching. So the asymmetrical stretching band comes at 1810 and the symmetrical stretching band comes around 1760. You should take this as a base value. I will tell you what is meant by a base value and how it is affected when conjugation and other phenomena take place. Now, acid chloride, for example, has the value of 1800 inverse centimeter. So, in fact, the anhydride and the acid chlorides are the highest stretching frequency values for the carbonyl stretching frequency, whereas the amide comes at the lowest stretching frequency value among the carbonyl functional group. The reason is explained as follows. Let us take the example of either an ester or an acid chloride. Let us take the example of the acid chloride. Now, the carbonyl functional group is connected to an electron withdrawing chlorine atom or a fluorine atom, depending upon the halide that you have in the acid halide. As a result of the inductive effect of the carbon halogen bond, the electron on the carbonyl carbon gets depleted, and this is compensated by the participation of the lone pair of electron from the oxygen, which further strengthens the carbonyl bond. Therefore, the bond order of the carbonyl bond in the case of an acid halide, or the bond strength or the force constant of the carbonyl bond in the acid halide is much more than, for example, in the case of ester, and that is the reason the acid halide comes at a higher frequency compared to the ester. Now, let us compare the ester and the amide. The ester comes around 1735, whereas the amide comes at a lower frequency of 1690. This is explained as follows. In the case of the ester as well as the amide, the same electronegativity plays a role in terms of the withdrawing nature of the heteroatom, namely oxygen and nitrogen in the case of ester and amide. However, this is going to be much less pronounced compared to a halogen because oxygen and nitrogen are less electronegative than the halogen atom itself. Now, in the case of oxygen, it is sufficiently electronegative to have this effect and thereby increasing the bond strength or the force constant of the carbonyl stretching frequency. So, that comes around 1735. In the case of the amides, there is another factor that needs to be considered, namely the delocalization of the lone pair of electron from the nitrogen onto the carbonyl functional group, which has the resonance structure here. From the resonance structure, you can tell that the carbonyl carbon oxygen bond strength or the bond order is decreased. So as a result of that, the stretching frequency also is quite a bit decreased compared to the ester. So one has to weigh out these two effects, namely the effect of electron withdrawing by inductive effect and the electron donation by means of a resonance effect. These are the two factors that needs to be weighed in. In the case of amides, this is a overriding factor, namely the delocalization and the resulting canonical structure is a overriding factor, whereas in the case of esters and acid chlorides, it is the overriding factor is the electronegativity and the inductively electron withdrawing nature of the oxygen and the halogen respectively, which pushes the carbonyl stretching frequency of acid chlorides and the ester much higher than the amides itself. So this is something consistently you will see in the entire spectroscopy or infrared spectroscopy of carbonyl compounds. The anhydrides comes at the highest stretching frequency value, and the amides come at the lowest stretching frequency values in the infrared spectrum. Aldehydes, ketone, esters and so on, they come in between region. The acid is a very special case because it depends on whether the acid is existing as a monomer or a hydrogen bonded dimer kind of a structure. In case of a hydrogen bonded dimer kind of a structure, it will come around 1710, whereas in the case of a monomeric acid functional group, it should come somewhere around close to the ester around 1730 or 1740 in that particular region. We will look into the effect of the hydrogen bonding and other electronic effect in the next few slides. Now the factors that contribute to the carbonyl stretching frequency, first we will consider the electronic effect. Now we are comparing, for example, the force constant dependency on the electron withdrawing nature of the groups that are attached to the carbonyl functional group. We are comparing acetone, trifluoroacetone and hexafluoroacetone. Now as you go from the acetone to trifluoroacetone, the trifluoro group is an electron withdrawing functional group that is going to deplete the electron density on the carbonyl carbon, thereby forcing the carbon oxygen bond to be strengthened by the participation of lone pair of electron from the carbonyl oxygen onto the carbon oxygen bond. And this effect will further increase when you have two trifluoromethyl groups. In other words, you should have twice the effect of the electron withdrawing effect of the functional group of CF3 group attached to the carbonyl. Therefore, if you look at the bond strength in terms of the carbon oxygen bond strength or the force constant, acetone will have the lowest force constant, whereas hexafluoroacetone will have the highest force constant, which is reflected in the form of the increasing frequency as you go from acetone to trifluoroacetone to hexafluoroacetone. Now if you compare, for example, an acid fluoride with acid chloride, the chlorine is less electronegative than fluorine, so the carbon fluorine bond is a much more electron withdrawing group, which again strengthens the carbonyl bond by the participation of the oxygen lone pair onto the CO bond in this particular case. And chlorine being less electronegative, the force constant in this chloride is going to be much less than the fluoride. So the acid fluorides also come at a high frequency compared to acid chlorides. Acid bromides has a very peculiar effect because the mass also increases, which will decrease the stretching frequency, and the electronegativity also decreases, which will also decrease the stretching frequency. So it could be actually a combination of two effects of mass effect as well as the electronegativity effect, which decreases the carbonyl stretching frequency as you go from carbonyl fluoride to carbonyl chloride to carbonyl bromides. Now the effect of conjugation on the carbonyl stretching frequency is discussed in this particular slide. Conjugation increases the single bond character. You can see from the resonance structure that is written here. An alpha beta unsaturated carbonyl functional group, this carbon oxygen double bond is no longer a double bond. It becomes a single bond in this canonical structure. So the actual bond order is less than 2 but more than 1. If that is the case, the stretching frequency should decrease because the force constant should decrease in the case of the conjugated carbonyl functional group. The conjugation could be because of an isolated double bond in conjugation with the carbonyl functional group, or it could be because of part of an aromatic system being conjugation with the carbonyl functional group. The lowering of the bond order and the lowering of the force constant, and hence the lowering of the carbonyl stretching frequency, is what one would normally observe. This is illustrated by the examples that are shown here. If we take non-aldehyde, which is C9 aldehyde, the stretching frequency of the carbonyl function, we are talking about the CO stretch in all these cases. It comes around 1730 inverse centimeter. And crotonaldehyde, which is an alpha beta unsaturated carbonyl functional group, comes around 1695. And benzaldehyde, which is also an alpha beta unsaturated system, except the alpha beta unsaturation comes from the phenyl group that is attached to the aldehyde functional group, that comes around 1700 inverse centimeter. So when we talk about base value, we are actually talking about the saturated compound base value, and whatever the electronic effect that may be, we add some numbers or subtract some numbers to get the actual values of the alpha beta unsaturated system, and so on. So in the case of the alpha beta unsaturated carbonyl functional group, the stretching frequency is lowered anywhere from 25 inverse centimeter to 45 inverse centimeter from the base value, which is normally is the value that is given with the carbonyl functional groups of various kind. In this particular chart it is given. This is the base value that we normally talk about. Now let us consider the example of para-aminoacetophenone, acetophenone and para-nitroacetophenone. The stretching frequency keeps increasing as you go from para-aminoacetophenone to para-nitroacetophenone. Now if you take acetophenone as the base value for the alpha beta unsaturated carbonyl system, this is correct at 1685. So from the base value of about 1720 or so, you have decreased it by about 40 or 35 inverse centimeter to arrive at the 1685. Now what happens when you have an electron donating groups in the para position? This is the kind of resonance effect the para amino functional group is going to have on the carbonyl para-aminoacetophenone. You can see the canonical structure has a carbon-oxygen single bond, and the other canonical structure has the carbon-oxygen double bond. So the bond order essentially gets decreased because of the electron delocalization onto the carbon-oxygen bond here. So as a result of that, the stretching frequency also decreases when you grow from acetophenone to para-aminoacetophenone. Now when it comes to para-nitroacetophenone, the para-nitro group is an electron withdrawing group, so that should essentially decrease or deplete the electron density on this particular carbon, and that in turn should the participation of the lone pair of electrons on the oxygen onto the carbon-oxygen bond should increase the force constant. So one gradually sees the increase in the stretching frequency of the carbonyl functional group as one goes from the para-amino, which is an electron donating group, to para-nitro, which is an electron withdrawing group. The effect of these electronic effects on the carbonyl stretching frequency is what is illustrated in this slide. Now the size of the ring also has a very peculiar effect in terms of the carbonyl stretching frequency. As you go from, let us first talk about the unsaturation or the conjugation of the carbonyl functional group. This is the alpha, beta, gamma, this is delta lactone, and this is gamma lactone. In the case of delta lactone, this is a 6-membered lactone, saturated lactone, and it is essentially an ester functional group. So 1735 is the base value because this molecule is devoid of any kind of a strain because it is a 6-membered ring. It comes around 1735. Now what happens when you do an alpha beta unsaturation to this molecule? In other words, this is unsaturated lactone. In this particular case, the value decreases by 10 inverse centimeter to 1725. And when you have the unsaturation closer to the oxygen of the lactone rather than closer to the carbonyl, in other words, this unsaturation is in conjugation with the carbonyl, whereas this unsaturation is in conjugation with the oxygen of the lactone. Under these circumstances, when you have an unsaturation along the carbon-oxygen carbonyl bond, in other words, this delocalization essentially reduces the bond order, and that is why the stretching frequency decreases, whereas this unsaturation next to the oxygen essentially allows the participation of the oxygen lone pair to be delocalized onto the vinylic system. Thereby, this oxygen actually acquires a positive charge, or it becomes electron deficient because of the delocalization, which in turn triggers the mechanism of pulling the electron from the carbonyl function oxygen to the carbonyl carbon-oxygen bond, thereby increasing the force constant of this particular carbonyl with respect to this carbonyl here. So an alpha beta unsaturated lactone is reduced by about 10 inverse centimeter from the base value, whereas the unsaturation when it is closer to the oxygen participation, lone pair of oxygen from this particular oxygen participating on the delocalization, as it is shown in the bottom resonance structure, the value increases because the force constant of this carbonyl is much higher than the force constant of this particular carbonyl. We will consider the decrease in the ring size and how it affects the carbonyl stretching frequency in a minute, but the trend what you have to see here is this is a saturated gamma lactone, this is an alpha beta unsaturated gamma lactone, this is a beta gamma unsaturated lactone, gamma lactone. So as you can see, from the 1770 it decreases to 1750, and from the 1770 it increases to 1800 for the same reason that we discussed in the case of the delta lactone, because of the two effects, namely the delocalization of the double bond onto the carbonyl functional group or the delocalization of the lone pair of electron onto the vinylic system, as opposite effects in terms of the stretching frequency is being reduced in the case of alpha beta unsaturation, and stretching frequency being increased if you have a beta gamma or beta gamma or gamma delta kind of an unsaturation, as the case may be. Now let us go to the effect of the ring size. A 6-membered ring with a carbonyl functional group is a relatively unstrained ring because 6-membered ring can accommodate the hybridization angle of 109 in the saturated carbons and 120 in the case of the carbonyl sp2 carbon, for example. This gives rise to the IR band at around 1710 to 1720 inverse centimeter, which is the base value normally taken for a saturated ketone, particularly of a 6-membered cyclohexanone kind of a saturated ketone. With the decreasing ring size, the carbonyl stretching frequency increases for the following reason. In order to accommodate small angles in the small rings that require the use of the p character more and to make the carbon-carbon bonds. In other words, the ring carbon-carbon bonds will have to acquire a larger contribution from the p orbitals rather than from the s orbital, because as you go from the larger size ring to the smaller size ring, the bond angle keeps decreasing. For example, the bond angle in the 6-membered ring can be 109, whereas in the 5-membered ring will be much smaller, whereas when you go to the 4-membered or 3-membered ring, it is going to be even smaller than the 109 angle. In the case of a cyclobutanone kind of a system, you have a 90-degree angle, whereas you have a cyclopropanone kind of a system, it will have 60-degree angle or so. So in order to accommodate the angle, the best way the molecule can cope with the strain is to increase the p character of the carbon-carbon bond. As the p character of the carbon-carbon bond increases, the s character of the carbon-oxygen sigma bond increases, and thereby strengthening the carbon-oxygen sigma bond in the case of smaller ring system. The force constant increases in the smaller ring system compared to the relatively unstrained 6-membered ring. A 3-membered ring will have a much higher s character of the carbon-oxygen bond, and as a result of the increase in the force constant, the frequency also increases. This is illustrated clearly in the following examples. The ring size effect is what is shown here. A saturated 6-membered ring is unstrained with a normal base value of 1715 for the ketone. When it goes to a 5-membered ring, there is about 30 inverse centimeter increase in the frequency, and when it goes to a 4-membered, it's about 35 inverse centimeter. So the 4-membered and 3-membered carbonyl groups are the highest value in terms of the carbonyl stretching frequency among the series of 6-membered, 5-membered and 4-membered. So when you go from, for example, the ketone to an ester, the frequency should increase. The ester has a higher frequency base value. So the alpha, beta, gamma, delta lactone has 1750 inverse centimeter. The gamma lactone has 1775 inverse centimeter, whereas the beta lactone has 1845 inverse centimeter. Now compared to a lactone, the amide should have a lower frequency. That is why it has lower. In case you can go vertically down or horizontally also. When you go vertically down, going from ketone to lactone increases the frequency. From lactone to amide, it decreases the frequency for the reasons that was discussed earlier. As you go across the row, in each row, the size of the ring decreases from a 6-membered to a 5-membered to a 4-membered, which increases the carbonyl stretching frequency within the series because of the higher strain of the ring and the larger participation of the s electron on the carbon oxygen sigma bond of the carbonyl systems in these cases. Now the hydrogen bond, usually carbonyl groups, for example in the case of salicylaldehyde or methyl salicylate kind of a ortho-functionalized system, one can have intramolecular hydrogen bond of this type. And what happens when a hydrogen bonding takes place to a carbonyl functional group? It essentially lengthens a carbonyl functional group's carbon-oxygen bond and thereby lowering the force constant. Therefore, the carbonyl stretching frequency is lowered because of the hydrogen bonding interaction. Now, if you consider methyl benzoate, this is an alpha beta unsaturated ester. So compared to a base value for the saturated ester, which is about 1740, this is 20 inverse centimeter lower, so it is 1720. And when it is undergoing a hydrogen bonding interaction with ortho hydroxy derivative, in other words, this is methyl salicylate is what we are referring to. Because of the intramolecular hydrogen bonding, it is further reduced to 1680. The intramolecular hydrogen bonding effect is beautifully illustrated in the case of the anthraquinones. Anthraquinone with a hydroxy functional group in the periposition can undergo this kind of hydrogen bonding interaction. So from the base value of 1678 for an alpha beta unsaturated carbonyl functional group in the case of anthraquinone, it reduces to 1647. There are two types of carbonyl groups. One is hydrogen bonded, the other one is non-hydrogen bonded. The non-hydrogen bonded essentially comes in the same region at 1675 like this one here, whereas the hydrogen bonded one is reduced by about 30 inverse centimeter to about 1647 or so. This is a doubly hydrogen bonded system. In this particular case, there are two stretching frequencies which are obtained. One is probably due to the carbon-carbon bond, double bond. The other one is because of the carbonyl stretching frequency, which is 1645. So one can see the hydrogen bonding essentially reduces the carbonyl stretching frequency to lower stretching frequencies in most cases. Now the effect of alpha halogen, there are two effects one can discuss. One is sheer electron withdrawing nature of the alpha halogen because of the higher electronegativity, which should push the carbonyl stretching frequency to higher values. In the case of cyclohexanones, you can have either an axial chlorocyclohexanone or an equatorial chlorocyclohexanone. In the case of axial chlorocyclohexanone, it is purely electron inductive effect is what is felt by the carbonyl functional group, which increases the force constant of the carbonyl functional group, thereby increasing the stretching frequency of the carbonyl functional group of the alpha chloro derivative. In the case of an equatorial isomer, equatorial conformer for example, the carbon chlorine dipole as well as the carbon oxygen dipole point in the same direction, so there should be a dipolar repulsion. As a result of the dipolar repulsion, the carbon oxygen bond has a higher force constant, and as a result of a higher force constant, it will have a higher stretching frequency value. This is clearly illustrated in the case of a rigid system which doesn't have this kind of a dynamic process. In other words, 2-chlorocyclohexanone can exist either in this conformer or in this conformer. In fact, the infrared spectrum will give you two bands, one corresponding to the axial chloro derivative, the other one corresponding to the equatorial chloro derivative. If the axial equatorial interconversion, chair-to-chair interconversion is frozen, as in the case of the decalone, then the axial chloro as well as the equatorial chloro are diastereoisomers, and they have independent existence and they can be separated, and separately they can measure the infrared spectrum. For the axial chloro derivative, it is 1725. It is close to the actual saturated compound, which is cyclohexanone, comes around 1710 or so. Whereas the equatorial chlorine derivative, because of the dipole-dipole repulsion that we talked about, it comes at a much higher delta value compared to the axial chloro derivative. So one can easily distinguish if two chloro derivatives are available, which one is axial chloro, which one is equatorial chloro can be easily decided by the carbonyl stretching frequency of the alpha halo derivatives of this kind. Now let us have a look at some representative examples of carbonyl compounds in infrared spectra. This is trans-cinnamaldehyde. Trans-cinnamaldehyde is an alpha-beta unsaturated system. So one can see the carbonyl stretching frequency at 1677, which is a very sharp and very intense band in this particular case. The CH stretching frequency of the aldehyde functional group. The aldehyde CH usually comes as two-line pattern, somewhere around 2800 inverse centimeter is where it comes. So you can see here 2800 inverse centimeter, you see a doublet kind of a thing because of the carbon hydrogen stretching of the aldehyde functional group. Otherwise, the alpha beta unsaturated C double bond C stretching is coming somewhere around 1600, which is this particular band, and because it is a monosubstituted derivative, the out of plane bending modes come in this particular region and so on. So this region essentially you don't interpret it very deeply. The most interesting feature in the spectrum is essentially the carbonyl stretching frequency and the aldehyde CH stretching frequency are the two most interesting ones. This is cyclobutanone spectrum. Cyclobutanone being a 4-membered ring system compared to a 6-membered ring system which is around 1710 or 1720, it comes at a much higher frequency value. 1780 is where it comes in this particular case, for example. And this is again an alpha beta unsaturated system because of the phenyl group. This is propiophenone. Propiophenone has a stretching frequency, carbonyl stretching frequency of 1688 because it is an alpha beta unsaturated compound. Please see here in the case of cyclobutanone, then there is no C double bond C unsaturation. You don't see any C double bond C stretching. This is a relatively free area. Whereas in the case of the phenyl derivative, the C double bond C stretching frequencies essentially appear in this particular region between 1600 and 1500. So one can clearly see it. One can also see the out of plane bending of the monosubstitute or aromatic system, which is coming in the region of 700 to about 800 or so in this particular region. Now this is isobutyric acid. Isobutyric acid, there are two unique features one has to observe. One is the carbonyl stretching frequency, which is coming around 1720 or so in this particular case, and that is a very intense band in this case, and it also should have two other recognizable bands. One because of the OH stretch, you can see here a very broad stretching frequency in the region of 2800 to 3200 inverse centimeter, which is this big envelope that you see here is essentially because of the OH stretching frequency. Carboxylic acids typically have very broad OH stretching frequency because of intramolecular as well as intermolecular hydrogen bonding interaction. And the one other feature one can see in the carboxylic acid spectrum is the CO single bond stretching frequency, which comes in this particular case around 1200 inverse centimeter or so. This is for benzoic acid. In addition to the carbonyl stretching frequency, you do see the C double bond C aromatic stretching frequencies also, plus the OH stretching frequency in the usual region, in the higher frequency region is very clearly seen. This is a spectrum of a primary amide. This is butyramide. Butyramide spectrum should have the carbonyl stretching frequency coming in this region. Now one has to discuss the amide a little more detail. The NH bending mode also comes in the same region around 1660 or 1640 or so, and it's anywhere between 1600 to 1640 the NH bending can also come. So the amides usually show two bands in the case of the carbonyl region. In the carbonyl region, one because of the actual carbonyl stretching frequency, the other one because of the NH bending kind of a mode of frequency. And this is called amide 1 band and this is called amide 2 band. That is how they are described in the literature. And the two bands can be merged, as in this particular case, for example. There is a overlap because of the broadening of the signal. One can tell that there is a overlapping of the NH and the CO bond. Now the amide functional group also has the NH stretching. And if it is a primary amide, we have seen earlier that it should come as a doublet. In fact, it does come as a doublet. Whereas if it is a secondary amide, as in this particular case, N-methylacetamide, for example, it comes as a fairly broad single line pattern is what one sees for the amide functional group, NH stretching frequency as well as the carbonyl stretching frequency. This is a spectrum of butyric acid anhydride. Butyric acid anhydride, for example, is very clearly it doesn't have the OH functional group, so that region is fairly clean. Only CH stretching frequencies are observed in this region. So compared to butyric acid, this is a very different spectrum. So when you take butyric acid and convert it into a butyric anhydride, it is easy to follow the reaction by an IR spectroscopy because the OH should disappear completely once the anhydride is completely formed. Now anhydrides also have two frequencies, one because of the asymmetric stretching, the other one is because of the symmetric stretching of the carbonyl functional group, which we have seen earlier. So the butyric anhydride also shows two bands. The highest band is 1819, which is a symmetric stretch, and the lower band is 1750, which is a symmetrical stretch. And this is a carbon oxygen single bond stretch is what is seen around 1000 inverse centimeter in this particular case. So what we have seen is a variety of carbonyl functional group. The various effects which affect the various factors which affect the carbonyl stretching frequency is what we have seen in the past few slides. Now let us look into another important functional group, namely nitro functional group. The two bands are usually seen for the nitro functional group also in the region for the N double bond O stretching frequency. Due to the N double bond O stretching frequency due to the symmetric as well as the asymmetric stretching of the N double bond O, which is represented pictorially below here for the nitro functional group. The bands are usually intense because there is a large change in the dipole moment during the stretching and compressing motion of the N double bond O, for example. As usual, conjugation reduces the frequency by about 20 inverse centimeter. In other words, aromatic versus aliphatic nitro compounds, if we compare, the aromatic nitro compounds will have about 15 to 20 inverse centimeter lower stretching frequency for the NO bond compared to an aliphatic nitro compound. This is the spectrum of a saturated long chain alkyl. This is the hexyl nitrohexane, for example, in this particular case. So one sees the CH stretching because there are a large number of CH bonds in this particular molecule. So CH stretching in the saturated sp3 CH stretching is what is seen around 3000 inverse centimeter or so. And there are two intense bands in this region between 1500 and from 1500 to about 1300. Now, whether carbonyl stretching frequency I forgot to mention. The symmetrical stretching frequency can come anywhere between 1390 to 1330. The asymmetrical stretching frequency can come anywhere between 1570 to 1540. In fact, it is easy to remember 1535 and 1350 are the numbers which are the base values one can take as for the nitro compounds. In this particular case 1530 and this case 1350. The two digits are simply inversed in the case of the two frequencies of the symmetric and the asymmetric stretching frequency of the nitro. So a saturated nitro compound has a stretching frequency coming around 1560 or so in this particular case, and another frequency almost close to 1400 is where it is seen. This is a asymmetric stretching and this is a symmetric stretching of the N double bond O. And when you have the alpha beta unsaturated system, as you can see here, this comes around 1530 or so, much lower than the value for the saturated nitro compound. And you have again two bands. In addition to that, because of the alpha beta unsaturated C double bond C, one can also see the C double bond C stretching of the aromatic system in this particular region. So this region now becomes fairly crowded because of the multiple stretching frequencies which are appearing in this particular region. This is as usual the monosubstituted out of plane bending mode of the aromatic system that we are seeing here. This is 2,4-dinitrotoluene. 2,4-dinitrotoluene again has two bands because it is an alpha beta unsaturated system. It is 1520 and 1340 are the two bands corresponding to the nitro functional group in this particular molecule. The other important functional group is the cyano or the nitrile functional group. The cyano or nitrile functional group typically come in the region of 2280 to 2240. As a single band it will come. Typically it will come around 2250. You can take this as a base value for the saturated nitrile. It is an intense to medium intensity band. It is not very intense in nature compared to carbonyl or compared to a nitro functional group. This is not as intense usually, but nevertheless it is an unmistakable region where it comes, so it should be possible to identify the cyano functional group from an infrared spectrum. As usual, the alpha beta unsaturated nitriles will have a lower frequency compared to the saturated nitrile system, and cumulines such as azide, for example, or isocyanate and isothiocyanate, they also come typically in the region between 2200 to 2100 at various at various frequencies it come, one should be able to identify. These are less common functional group as far as organic chemists are concerned. Acide may be a common functional group, but isocyanate and thioisocyanates are not as common as the cyanofunctional group or the acide functional group in organic chemistry. Now the nitrile, there are two examples given here. Butyronitril and benzonitrile are the two compounds that is given here. This intense band that one sees around 2200 something frequency is because of the cyano stretching frequency. The C triple bond N stretching frequency actually comes at a lower frequency than a C triple bond C stretching frequency. The C triple bond C stretching frequency comes at a lower stretching frequency compared to a C triple bond N stretching frequency, because nitrogen is a heavier element in this particular case. The only difference is the C triple bond C, sometime one can miss it if it is an internal acetylene, because there won't be any dipole moment change. So the intensity of the C triple bond C is usually weak compared to a C triple bond N kind of a stretching frequency. In the case of alpha beta unsaturated system, in addition to the C triple bond N, one also see the C double bond C stretching frequency in the normal region of 1600 to 1400 inverse centimeter, and this is a monosubstituted out of plane bending mode of the monosubstituted aromatic system, which is seen as a doublet usually in this region. This is an acide. This is phenyl acide. Phenyl acide has a very intense band around 2111. This particular band here is because of the N double bond N stretching frequency. This is actually a cumulene kind of a system. Cumulines also come in this region of cyano and acetylene kind of a region is where the cumulene also comes. So this is acide peak. N double bond N stretching frequency is what is seen as a cumulene system around 2111 in this particular case. So what we have seen in this module are the important functional group, particularly carbonyl functional group, the various factors that affect the carbonyl stretching frequency, and we have seen why the variation takes place within the carbonyl stretching frequency for going from anhydride all the way to amide, how the frequency is affected by the electronic factors. Then we saw some examples of nitrile and nitro functional group, and one example of an azide functional group was also seen. Thank you very much for your attention.